We have described when a pair of vectors are considered orthogonal. In this video, we're going to talk about when a set of vectors is orthogonal. So suppose we have some set of vectors v1 all the way up to vr, and this lives inside of Fn dimensional space there. We say that the set v1 up to vr is orthogonal. It's an orthogonal set if each pair of distinct vectors is orthogonal. That is, if vi dot vj equals 0 whenever the indices I and j are different from each other. So that's what we mean by an orthogonal set. So a quick example of this. So let's take three vectors. We'll say v1, v2, and v3. I claim that the set v1, v2, v3 is an orthogonal set of vectors. And we can see that by just the quick calculations there. What happens when you take v1 dot v2? You're going to get 1 plus 2 minus 3, which is equal to 0. So that's an orthogonal pair. If I take v1 dot v3, and that one you're going to get negative 5 plus 8 minus 3, that's likewise 0. So v1, v3 is also an orthogonal pair. So v1 is orthogonal to v2 and v3. But to be an orthogonal set, every pair must be orthogonal. So the last pair we have to check is 2 and 3. It doesn't matter who goes first or who goes second, even with complex vectors. If you get 0 one time, if you flip it around, you'll get 0 the other time as well. So v2 dot v3, you get negative 5 plus 4 plus, it's a double negative, so it's a plus 1. So we're going to get 0 right there. And so this, in fact, shows that this is an orthogonal set of vectors. If any pair was not 0, if any pair was not 0 here, then that means those two vectors are not orthogonal, and hence the whole set is not orthogonal with each other. Now, one important caveat I have to mention here is when we define a set of vectors, we actually require that this be a non-zero set of vectors when we define orthogonal sets. And why is that? Well, like I mentioned before, the 0 vector is in fact orthogonal to everything, and it's quite exceptional in that regard. And as such, we have to remove the 0 vector from consideration when we talk about orthogonal sets, because 0 is going to be orthogonal to everything. And so we do have to treat it exceptionally. We're going to see why that is in just a second later on in this video. But we require that when we define orthogonal sets that all the vectors be non-zero. And there are some special cases of orthogonal sets I want to make mention to you. We saw an example of an orthogonal set of size 3. If you just have a single vector right here, a single vector just by itself is considered orthogonal. This is considered an orthogonal set if and only if v is not equal to 0. Because if it were equal to 0, orthogonal sets are not allowed to have the 0 vector, and so any vector that contains the 0 vector, or any set of vectors that contains the 0 vector cannot be orthogonal, so it's ruled out automatically. But even if it's non-zero, then you just have one vector. And so what about the pairs? Well, the definition here says that each pair of distinct vectors is orthogonal. If you have just a single vector, there are no pairs of vectors, and therefore there are no pairs which are not orthogonal. This is sort of like a little bit of logical acrobatics here, but a single vector by itself is vacuously orthogonal because there's not a second vector for which it's not orthogonal to, and since there exists no counterexamples, it's considered orthogonal. So the single vector by itself is an orthogonal set. That's something I want to mention here. Also, if you take the empty set is also considered an orthogonal set for the same reason, that there's no vectors inside that set. And so in particular, there's no pairs of vectors that come from the empty set. And so since there's no pairs, there exists no pairs which are not orthogonal. There's no dot products that give you non-zero. So a single vector is considered orthogonal. The empty set is considered orthogonal. But then if you have 2 or more, you do have to check, like we did in this example right here, on why. You have to check to make sure the pairs are 0 or non-zero. To be orthogonal, each of these dot products has to be 0. So, okay, why is it so important that we throw out 0? Sure, 0 is exceptional, but I could throw 0 in there and it's not going to complicate the issue, is it? Well, it turns out that the main reason we don't want 0 to be considered an orthogonal vector, that is, we don't want a set containing 0 to be orthogonal, is the following. If S is a set of vectors, we'll say v1 up to vp inside of Fn. If this set is orthogonal, and these are all non-zero vectors, then S is actually an independent set. And this is a pretty cool argument here that if we were trying to show that these vectors are linearly independent, we have to take some scalars like C1 V1 plus C2 V2 all the way down to CP VP, right? This is equal to the zero vector. If you want to show this set of vectors is linearly independent, we then check, are there any linear combinations that produce the zero vector? And I claim that there aren't going to be any. And so what you do is you're going to pick your favorite vector inside this list. We'll take VI right here, and we're going to dot it with everything in this calculation right here. VI dot 0 on the right, VI dot everything else on the left. Well, by properties of the dot product or the Hermitian product or whatever your inner product is, we can distribute this into all the pieces. So we end up with VI dot C1 V1, and then you're going to get the next one, VI dot C2 V2, right? And then you continue down in this list, right? At some point in the list, though, you're going to get VI dot CI VI, so it's going to be dotted with itself, and then you continue on till the very end, VI dot CP VP. Now the right hand side is going to be easy. If you take any vector dot 0, you're going to get 0 like so. Each of these scalars can come out here. We can factor each one of these scalars out, again, by properties of the inner product there. So you're going to get C1 times VI dot V1. Right, and you continue down this list. Like I said, somewhere in this list, there's going to be the ith position, CI times VI dot VI, like so. And then you get all the way down to the end. Whoops. You get a CP times VI dot VP. Now, by assumption, this is an orthogonal set. So as long as you pick different vectors, the dot product should be 0. So this inner product is 0. The second one, the third one, they're all 0. The pth one is 0. They're all 0 with the exception of this one right here, VI dot VI. We have no assumption about what happens when you dot the vector with itself. So the left-hand side becomes CI times VI dot VI, like so. And this is going to equal 0. So we have a product of two numbers. There's CI, which is a scalar, and then VI dot VI, which is a scalar. And so we have the product of two numbers that equals 0, so the zero product property applies. We either get CI equals 0, or we get that VI dot VI equals 0. But it turns out this second condition is impossible because we have an inner product. We have the positive definite condition. The only way that the inner product of a vector with itself equals 0 is if that vector was 0. Aha! This is why we actually care so much about the vectors to be non-zero. We need it to prove that orthogonal sets are actually linearly independent. And so since the dot product is not 0, that means the scalar was 0. And so then if we come back to our original equation right here, then it turns out that one by one, each of these scalars must have been 0. And so the only solution to this homogeneous system was the trivial solution. And that's exactly what one expects when you have a linear independent set. The only way to get this combination to be 0 is to be the 0 itself. So orthogonal sets are in fact linearly independent, but we have to make sure that we only have non-zero numbers. If we throw in the 0 vector, it doesn't obstruct the orthogonal condition per se, but it will affect the linear independence, which we want orthogonal sets to be linearly independent. For the following reason, if orthogonal sets are linearly independent, automatically, if our orthogonal set is then a spanning set, then we can construct what's called an orthogonal basis. A basis, remember, is a linearly independent spanning set. Well, what if our basis is orthogonal? For example, the standard basis for Fn is orthogonal. And you can see that because your usual vector is EI, right? This is the vector with a 1 in the ith position. It's got zeros everywhere else, right? The standard base is an orthogonal basis, and we are going to like orthogonal bases better than just regular bases. There's some benefits we get from being orthogonal. One of them, which is that orthogonal sets are automatically linearly independent. Another thing I want to mention here is we say that a set of vectors is orthonormal if if the set is orthogonal and every vector inside of the set is a unit vector. Remember, a unit vector means that the length of the vector is equal to 1. So an orthogonal set of unit vectors is called orthonormal. And the reason we call it orthonormal here is that orthonormal is this amalgamation between the word orthogonal and the word normal. Remember that if you take any vector, any non-zero vector v, and you divide it by its, if you take any non-zero vector v and you divide it by its norm, then that will give you a unit vector. This is a unit vector here. And so this is the process of normalization. So if you take away the norm, the length of the vector, you get this normalized vector, a unit vector. So orthonormal will be those sets of vectors which are orthogonal and consist only of unit vectors. And so therefore we can also talk about the idea of an orthonormal basis, which are going to be some of our favorite bases in existence, right? And what a shocker, the standard basis for Fn is the canonical example of an orthonormal basis. We'll see in the future the benefit of orthonormal bases, which we can construct if we can come up with orthogonal sets that span.